There is a question that keeps more people out of AI than any other, and it is usually asked in a whisper: how much math do I actually need? The fear behind it is a wall of Greek letters. The assumption that real AI work sits behind a graduate degree. This episode tears that wall down. Here is the secret of the whole course you have just watched. Every single episode was quietly running on a small set of ideas from math and computer science, about 8 of them, and you already understand most of them without knowing their names. By the end of this episode, you will know what those 8 are, where you already met each one, and which parts of AI math you can genuinely skip. This is the episode that turns fear into a checklist. Quick note before we dig in. If you find this useful, subscribe and drop a topic you want explained in the comments. Now let us get into it. Start with the one concept that carries more of modern AI than any other: the vector. You met it properly in the Embeddings episode, a list of numbers that places a meaning at a point in space. That is truly all a vector is, an array of numbers treated as a position, or as an arrow from the origin to that position. King is a point. Queen is a nearby point. The entire trick of embeddings is that distance in this space means difference in meaning, which raises the question the whole retrieval arc of this course depends on: how do you measure nearby? One formula. The dot product, multiply the vector's numbers pairwise and add them up. And its normalized cousin, cosine similarity. Cosine similarity asks, do these two arrows point the same direction? Same direction, score near 1, same meaning. Unrelated, score near 0. If there is one piece of math worth doing by hand once on paper, it is this: 2 small vectors, multiply, add. 30 seconds. That 30 seconds is the operation your RAG pipeline from episode 14 performs every time it retrieves a document. It is also what your vector memory from episode 29 does every time an agent recalls you. One formula, half the modern stack. Now stack vectors in rows and you have a matrix. Multiplying by a matrix transforms every vector at once, stretching and rotating the whole space. That is what a neural network layer is, a stored transformation learned during training. And the attention mechanism from episode 6? Queries, keys, and values are just 3 matrix multiplications applied to your tokens. You do not need to push the symbols yourself. The library does it. What you need is the picture. A model is a long pipeline of learned transformations, each one a matrix, reshaping meaning step by step. That picture is 90% of the linear algebra you will ever need, and you just got it in 90 seconds. Next, probability, and you have been using this one since episode 5. A language model's raw output is a score for every token in its vocabulary. A function called softmax squashes those scores into a probability distribution, everything between 0 and 1, summing to 1. Temperature, top P, all those creativity dials you learned? They just reshape this distribution before a token is drawn from it. Flatten it, the model gets adventurous. Sharpen it, the model gets predictable. When a model hallucinates confidently, you now know what that means mechanically. The distribution was sharp, the model was certain, and it was also wrong. Certainty and correctness are different axes. That single insight is most of the probability you need. Now cross from math into computer science, because data structures are where AI systems live, and the first one is hiding inside a phrase you have heard since the caching episode, the KV cache. K and V keys and values. A key value store, the hash map, is the most useful data structure in computing. Look up a value directly by its key, no searching. Tokenization from episode 2 is a lookup table, text chunk in, token number out. The KV cache is the attention machinery keeping each token's computed key and value so it never recomputes them, which is exactly why prompt caching from episode 35 saves real money. One humble data structure, billions of dollars of inference savings. The second structure is the graph, nodes and edges. You have met it 3 separate times wearing 3 costumes. GraphRAG, episode 17, entities as nodes, relationships as edges, so retrieval can walk connections instead of just matching similarity. LangGraph, episode 25, an agent's workflow as nodes and edges, so loops and branches are explicit. And the A2A episode, agents as nodes in a network, messages as edges. When you see graph anywhere in AI, it is the same picture, things, and the connections between things, and the payoff is always the same. You can walk the connections. Then there is the queue, first in, first out, which is how multi-agent systems from episode 26 pass messages and how every production API absorbs a burst of requests without falling over. And the tree, nested structure, which you touch every time an LLM returns the structured JSON you learned to demand in episode 11. You do not study these, you just recognize them on sight. Now, the one genuine algorithm this course owes you, because episode 15 promised the vector database was fast and deferred the how. Here is the how. The naive way to find the nearest vector among 100 million is to compare against every single one, linear time, unusably slow. The fix is a beautiful idea called approximate-nearest-neighbor search, and the reigning algorithm is HNSW, hierarchical navigable small world. The picture: build a highway system over the data. The top layer is sparse, a few long-range links, like flying between hub cities. Each layer down gets denser and more local regional roads than neighborhood streets. A search starts at the top, hops long distances toward the target's region, drops a layer, refines, drops again, and lands on the nearest neighbors having checked only a tiny fraction of the data. The trait is in the name: approximate. You get near-perfect results at a fraction of the cost, which is exactly the trait retrieval wants. That is the entire magic of Pinecone, Chroma, and Friends. Cosine similarity for the measuring, HNSW for the finding. One last piece of literacy ties it together: big O notation, which is just a way of saying how cost grows as input grows. You already felt it twice. Attention compares every token with every other token, n squared, which is why doubling your context more than doubles your cost, and why the context engineering episode told you long context rot. And brute force search grows linearly while HNSW grows roughly logarithmically, which is why vector databases scale and grep does not. You do not need to derive complexity classes. You need the reflex: when n doubles, what happens to the bill? And what about the famous stuff you were dreading? Calculus, gradients, backpropagation? Here is the honest boundary. Gradient descent, the engine of all training from low RA to the RLVR episode, is one intuition. Measure how wrong the model is. Feel which direction each weight should nudge to be less wrong. Nudge. Repeat a few billion times. Rolling downhill in fog, one step at a time. If you build applications, RAG, agents, products, that intuition is genuinely all you need, because the libraries handle every derivative. You only need the real calculus if you intend to do research or build training systems themselves. Knowing where that boundary sits and that you are allowed to stand on the application side of it is the most freeing fact in this field. So, how does this land depending on who you are? As an individual, this is your permission slip. The math wall is a myth for application work, and the 8 ideas in this episode: vector, cosine, matrix as transformation, distribution, hash map, graph, ANN search, and the n-squared reflex, are learnable in a weekend because you already met them all in context. As a startup, this vocabulary is a hiring filter and a debugging tool. An engineer who knows why retrieval is approximate and why context costs n-squared will design systems that scale. One who does not will discover it in your cloud bill. And as a large enterprise, this is the shared language that lets your data scientists and your application engineers stop talking past each other. The difference between the model feels off and the distribution is too flat. Sharpen the sampling. Let us bring it home with the recap. What you learned today: vectors place meaning in space, and cosine similarity measures it, the one formula of the AI era. Matrices are learned transformations, and a model is a pipeline of them. Softmax turns scores into the probability distribution your temperature dial reshapes. Hash maps power tokenization and the KB cache. Graphs power GraphRAG, LangGraph, and agent networks. HNSW's layered highways make vector search fast by being approximately right. And the n-squared reflex explains half the cost structure of this industry. None of it needed a degree. It needed the 45 episodes of context you already have. The frontier will keep moving, and now you have the machinery underneath it. Subscribe, and I will keep taking it apart with you, all the way down to how it actually works. That is the core of it. If this helped, hit like and subscribe, ring the bell for the next deep dive, and tell me in the comments what you want broken down next. Thanks for watching.